Welcome friends. Today we talk about solve one tutorial problem related to boiler efficiency determination by indirect method. Now today we talk about one boiler which is a coal fired boiler. It's one type of solid fuel type boiler. And the problem is the following are the data collected for a boiler using coal as the fuel. Find out the boiler efficiency by indirect method. The data for calculation is fuel firing rate equal to 5600 kg per hour, steam generation rate equal to 21940 kg per hour, steam pressure 43 kg per centimeter square, steam temperature 377 degrees Celsius, feed water temperature 96 degrees Celsius, and percentage of CO2 in flue gas as 14% and percentage of CO in flue gas 0.55%. Average flue gas temperature is 190 degrees Celsius and ambient temperature is 31 degrees Celsius. Humidity in ambient air is nothing but specific humidity is taken from psychrometric chart equal to 0.0204 kg per kg of dry air. Then the surface temperature of boiler 70 degrees Celsius, wind velocity around the boiler 3.5 meter per second, total surface area of boiler 90 meter square, gross calorific value of bottom ash 800 kilocalorie per kg, and gross calorific value of fly ash 450 kilocalorie per kg, and ratio of bottom ash to fly ash is 90 is to 100. Then fuel analysis. In that fuel, ash content is 48% and moisture content 4.4%, carbon content 36%, hydrogen 2.6 and nitrogen 1.1 and oxygen 7.3 and sulfur 0.6 and gross calorific value of coal equal to 3501 kilocalorie per kg. These are the structure of fuel. Then the first step is the calculation of theoretical air requirement. Already the procedure to find out the boiler efficiency by indirect method is discussed in previous lecture. Therefore, we can directly go to the calculation. This is the formula for theoretical air requirement. Okay. Here carbon and hydrogen and oxygen and sulfur content available in the fuel is given. If I substitute the values by percent, then we get the theoretical requirement. The theoretical air having oxygen which is completely utilized for combustion. Okay, which is the meaning for theoretical air requirement, for which is equal to 4.79 kilogram of air per kilogram of coal. Okay, then step 2 is find the theoretical CO2 percent to calculate the excess air supplied. Okay, uh, the percentage of CO2 at theoretical condition equal to moles of carbon divided by moles of N2 plus moles of carbon plus moles of sulfur during the combustion. Okay, the nitrogen is available in fuel as well as air, but the nitrogen is doesn't react with any combustible material and is escaped from the boiler through chimney. Okay, sulfur is converted to sulfur dioxide and carbon is converted to carbon dioxide and hydrogen is converted to hydrogen H2O as water in the stage of superheated steam. Okay, but nitrogen is doesn't react any combustible materials, therefore it releases nitrogen only. Okay, then where moles of nitrogen equal to nitrogen, I already said nitrogen available in fuel as well as air. Therefore, the weight of nitrogen in theoretical air divided by molecular weight of N2 plus and weight of nitrogen in fuel divided by molecular weight of N2. We already know the mole equal to weight divided by molecular weight. This is the formula from properties of gas. Okay, you can refer that also. Then moles of N2 equal to substitute the values there. the fraction is 77 divided by 100, which means the atmospheric air having 77% nitrogen and 23% oxygen. This is the common structure of atmospheric air. In that, the 77% only is nitrogen. Therefore, the 4.79 theoretical air having that 77% alone nitrogen. Therefore, that fraction is multiplied with that theoretical air requirement. Okay, then divided by 28 plus 0.011 is available in fuel. Therefore, finally we get the moles of N2 equal to 0.1321. Then moles of carbon is the carbon content is given in the problem, which is equal to 36%. Therefore, by substituting the in terms of fraction, is equal to 0.36 divided by molecular weight, we get 0.03. Then similarly, we can calculate the moles of sulfur. Is equal to 0.006 is given divided by molecular weight equal to 0.0001875. Then substitute the above values in formula, then we can get the theoretical theoretical CO2 emission in flue gas. Okay, but in that problem they are giving the actual measured CO2 in flue gas equal to 14%, which is used to find the excess air supplied using the formula excess air supplied equal to 7900 into CO2 theoretical and CO2 actual divided by CO2 plus actual into 100 minus CO2 theoretical. Substitute the theoretical and actual values in that formula, then we get the excess air supplied as 31% of theoretical air. In another way to find out the excess air supplied is using amount of oxygen molecule available in the flue gas, which is another method, but in that problem they are not giving, they are giving only CO2%. Therefore, through that formula itself we can calculate the excess air supplied percent. Then the next step is to find the total air supplied. Actual air supplied equal to 1 plus percentage of excess air into theoretical air supplied. In substituting the excess air value, then we can get the 6.27 kilogram of air per kg of coal. Okay, then step 5, to find the actual mass of dry flue gas. For simplified calculation, we can assume mass of dry flue gas equal to actual air supply. But exact calculation, we need that formula, which is equal to mass of CO2 in flue gas and mass of N2 content in fuel and mass of N2 in combustion air supplied and mass of oxygen in flue gas and mass of SO2 in flue gas. Here, mass of CO2 in flue gas is equal to percentage of carbon content available in the fuel divided by 100 into molecular weight of CO2 divided by molecular weight of C. And mass of N2 content in fuel is equal to percentage of N2 content in fuel divided by 100. Then mass of N2 in the combustion air supplied is actual mass of air supplied and the mass fraction for air, which is equal to 77 divided by 100. Then mass of O2 in flue gas, the theoretical air having CO2 that is completely used for combustion. Then the difference between actual mass of air supplied minus theoretical air supplied having oxygen only escape from the boiler. Therefore, we can differentiate that values. Then mass of SO2 in flue gas, similar calculation like that mass of CO2, then substitute the percentage value and substitute the molecular weight, then we can get the mass of SO2 in flue gas. By adding these all values, we can get the mass of dry flue gas. Then next step is set the value is 6.51 kilogram of dry flue gas per kg of coal. Okay, then the next step is to find all the losses. Okay, then first loss is heat loss in dry flue gas, which is L1 equal to mass of dry flue gas into Cp of dry flue gas into Tf minus Ta divided by gross calorific value of fuel into 100. and the mass of dry flue gas is already calculated, and Cp of flue gas is given, and exhaust flue gas temperature is given, and ambient temperature also known. Then substitute the values and we get the loss equal to 7.1%. Then the next loss is the heat loss due to formation of water from H2 in fuel. That H2 is present in the fuel during combustion. That H2 is reacted with oxygen and produce superheated water vapor, and which is escaped through by chimney. Okay, therefore which is also another one type of loss. Then substituting the H2 present in the fuel, and the specific heat of superheated water vapor is available, and flue gas temperature and ambient temperature. By substituting these values we can get the loss which is equal to 4.36%. Then next loss is heat loss due to moisture in fuel. Okay, in previous loss is related to moisture, sorry, hydrogen atom present in fuel, but this here the loss due to moisture present in fuel. During the combustion, the moisture is vaporized and escaped from the boiler through chimney. Therefore, substitute the moisture present in fuel in that formula, and specific heat of superheated water vapor and flue gas temperature and ambient temperature, we can get the loss value equal to 0.82%. Then next loss, heat loss due to moisture in air. Okay, because everybody knows the atmospheric air having less amount of moisture. Therefore that moisture is during combustion it's hot and escape from the boiler through chimney. Okay, then the value is equal to actual air supplied in the specific humidity in the specific heat of superheated water vapor and flue gas temperature minus ambient temperature divided by gross calorific value into 100. Substituting all known values, then we can get the loss equal to 0.25%. Then next loss is due to partial conversion of C to CO. The complete combustion means the carbon react with oxygen to produce CO2 and energy, which is the formula for complete combustion. But in some abnormal condition, that carbon produce CO, which is nothing but carbon monoxide, which release less amount of energy when compared to CO2 production. Therefore, which is the another type of loss. Then the percentage of CO and percentage of CO2 available in the flue gas is given in the problem. By substituting the values, we can get the loss which is equal to 2.2%. Then next loss, heat loss due to radiation and convection. In previous lecture, I told the calculation for radiation and convection loss is very difficult. Therefore, we can assume the loss value for various type of boilers from 1 to 2%. But in that problem, they are giving some data to calculate the radiation and convection problem. Therefore, we can substitute the values and calculate the exact amount of loss. Okay, here Ts is surface temperature of boiler and Ta is ambient temperature of boiler, and the square root of Vm, the velocity of around the boiler. Those data are available in the problem. Then substitute the values. The radiation per meter square equal to 937.62 watt per meter square. In that problem, they are the 0.86 is the conversion factor from watt to kilocalories. Okay, then it is equal to 806.35 kilocalories per meter square. That surface area of the boiler is given, therefore multiplied with this value, then we can get the total loss of boiler equal to 7257.6 kilocalorie per hour, which is the radiation loss per hour. Then the loss in terms of percentage is equal to 72571.6 into 100 divided by mass of fuel flow rate into calorific value of fuel. Mass of fuel flowing rate is equal to 5600 kilogram per hour, and 3501 is a gross calorific value of the fuel. Then we can get the loss equal to 0.37%. Therefore, we can directly assume 0.5%. It is not. It is which is used to simplify the calculation. But in that problem, they are giving the relevant data. Then only we can calculate. Then only we calculated the values. And up to in that problem, the fuel is coal, which is solid. Therefore, another two losses are available, which is the form of fly ash and bottom ash. The first one is heat loss due to unburned fly ash. The fly ash having low density, therefore it is passed away through chimney. Well, in that coal, the ash percentage is 48%. The ratio of bottom ash to fly ash equal 90:1. Therefore, gross calorific value of fly ash equal to 450 is available. Calorie per kg is available in that problem, and the amount of fly ash in 1 kg of coal equal to 0.1 into 0.48%, which is equal to 0.048 kgs. In that 0.48 kgs, the amount of fly ash equal to 90%. Sorry, heat available in the fly ash equal to 0.048 into 450. This is equal to 21.6 kilocalories per kg of coal. Then heat loss in fly ash equal to 21.6 into 100 divided by 3501, which is equal to 0.62%. Okay, because in that 48%, only 10% itself fly ash. Then remaining 90% is a bottom ash. Therefore, the heat loss for fly ash is equal to 0.62%. Then next loss is heat loss due to unburned bottom ash. Similarly, gross calorific value of bottom ash is given, which is equal to 800 kilocalorie per kg, and the amount of bottom ash in 1 kg of coal equal to 0.9 into 0.48, because 48% is the total ash available in the coal. In that, 90% is bottom ash and 10% is fly ash. The heat loss due to fly ash is already calculated. The remaining 90% is the bottom ash. Therefore, the bottom ash value is equal to 0.438 kg. And the heat loss in bottom ash equal to 0.438 in calorific value. Then we get 345.6 kilocalorie per kg of coal, and heat loss in bottom ash which is equal to 345.6 in 100 divided by gross calorific value of fuel. Then we get 9.87%. Okay, which is the significant amount of loss. We calculated all the losses for solid fuel fired boiler. Then the boiler efficiency by direct method equal to 100 minus all losses. Then substitute the all losses, we get the boiler efficiency, which is equal to 74.41%. Then the summary sheet of heat balance for coal fire boiler equal to the heat input is 3501 calorific value per kg of coal, and all other values also per kg of coal. Therefore, it is independent of amount of fuel firing. Therefore, the dry flue gas is equal to 248. Likewise, the all other losses are listed and the percentage of losses are listed. Then the boiler efficiency equal to 100 minus all losses, which is equal to 74.41%. We can add this all values, which gives that percent. Okay, which is the basic concept of indirect method boiler efficiency calculation. Okay, in next class we solve another one problem related to oil fired boiler. In that oil fired boiler, the ash content is negligible. Therefore, the losses L7 and L8 is negligible. Therefore, the boiler efficiency reduced with 100 minus 6 losses, up to 6 losses. Okay, thank you.